Yes, hello, is this audible?
Yes, teacher.
So, see, we had done the revision of atoms, nuclei, and now from modern physics, your dual nature of radiation and matter is there. So, the first topic that comes under this is your photoelectric effect. So, in photoelectric effect, what happens? When light of suitable frequency illuminates a metal surface. This is your metal surface, and light of suitable frequency illuminates your metal surface. Then electrons are ejected from the metal surface, and this phenomena is known as photoelectric effect. So this phenomena of photoelectric effect was initially observed by Hertz. There he demonstrated that UV light rays were falling on zinc plate. So photoelectrons got emitted. And then these photoelectrons conducted photoelectric current. When a setup was set, which you have studied in current electricity in your term 1, a battery was there, ammeter was there, which measured in microamperes, and then the UV radiation, UV light rays struck over it, and photoelectrons got ejected. So electrons moved, and this generated photocurrent. So photoelectrons, these electrons are known as photoelectrons, and the current generated by them is known as photoelectric current. Now see, few graphs you have to remember. One is your intensity, effect of intensity on light, and photoelectric current. So if this is your photoelectric current, this is your intensity of light. So photoelectric current is directly proportional to intensity of light. Means the number of photoelectrons emitted per second is proportional to the incident of the radiation, incident radiation. So this will be a straight graph like this. Now see, effect of potential you have to remember. Effect of potential in this manner. Now see, if this is your photoelectric current, this is y-axis represents your photoelectric current, and this is your anode potential. This is your anode potential V. So what happens? This increasing accelerating potential. What happens? Your photoelectric current increases till the initial accelerating potential. And a stage is reached when it becomes maximum in this manner. A stage is reached where it becomes maximum. So photoelectric current becomes maximum and does not further increase the intensity or increasing potential. So the maximum value of photoelectric current over here, this is known as the saturation current. This is known as the saturation current. Now see, if you have various numbers of these graphs on a single, various values drawn on a single graph. Let's say this is I1, this is I1, this is I2, this is I3. So order of I1, I2, and I3 becomes in this manner. This will be the greatest. I3, then I2, then I1. So you can get different values over here and you can be asked to compare them in this manner. Then the third graph that you have, also from this graph, you have to remember this formula. Kinetic energy maximum. This is equal to half mv square. In general, what do we write the formula of kinetic energy? It is half mv square. So if we have to take maximum kinetic energy, then you have to take maximum velocity. So this becomes half mv max square, which is equal to electronic charge multiplied by the stopping potential. Stopping potential is this. This is the stopping potential. One more graph that you have to remember is the effect of frequency of incident radiation on this stopping potential. So see, if you get such a graph, then how will you plot it? So this y-axis again represents your photoelectric current, and this represents your anode potential again. This is your x-axis, which represents anode potential once again. Now see, if different retarding potentials are provided to you, then what happens? Once the experiment is repeated, then different values of retarding potentials are obtained, like minus potential 1 V naught, minus V naught 2, minus V naught 3, and so on. So all these combine together and ultimately give a single photoelectric current in this manner. And this becomes constant. So this portion of photoelectric current, which is stable now, this is known as the saturation current. Now this will be the saturation current. The last graph regarding the stopping potential and the frequency that I was talking about. See, if this is your stopping potential, V naught, and this is your frequency of incident radiation. So if you plot a graph between frequency of incident radiation and corresponding stopping potential for different metals, you get a straight line in this manner. For different metals, you get straight line. So if you have metal A, this is for metal B, this is for metal C, you get into this manner. Now see, if you exceed the graph, if you extend the graph downwards, then on this y-axis only, if you extend it, this point, this is known as minus of phi naught, means your work function. This minus phi naught means your work function. All right. So this is the basic revision of your photoelectric current from photoelectric effect from your dual nature of radiation and matter. You have to remember the energy of a photon, h nu, which is equal to h nu, or which is equal to hc by lambda. Then number of photons emitted, you should remember, that is P divided by E, number of photons emitted per second. And momentum of photon also you should remember. Momentum of photon is what? P is equal to mv. Now see, photons move with the speed of light. So instead of V, you can write mc, which can be again written as h nu by c or h divided by lambda. Apart from this work function, you should remember work function is what? Work function is equal to h mu naught, where this is the threshold frequency. All right, then rest of basic formulas remains it. Let's practice some questions then. See, you have energy with you. Relate energy with frequency. You have a relationship between energy and frequency. Apply that formula. See, energy is what? Energy is equal to h multiplied by nu, where nu is this frequency. This is Planck's constant. This is energy. So now see, only frequency is only unknown. Energy is given, Planck's constant, you know. So frequency will be what? Energy divided by Planck's constant. So frequency will be energy. So energy, you cannot write it as 66.3 electron volt. You have to convert it. So you will write 66. No, not 10 to the power 34. See, this will be, did you convert it? 66.3 into 1.6 into 10 to the power minus 19 joules divided by 6.6 into 10 to the power minus 34. So see, this will be almost get, this will also almost get cancelled. You will be left with 1.6 and this will be 10 to the power 16 hertz. All right, just note it down. We'll do more questions.
I didn't convert into that.
Electron volt into joules. Or
I didn't convert.
okay. See, you should get the answer in SI unit. No? So convert everything, all the units that you have in terms of standard international units.
So we have to convert into EV.
See, power is given in SI unit only. Frequency is also given in the SI unit. All right, power's SI unit is what, and frequency's SI unit is hertz.
So first, like we have to convert E is equal to like energy. We have to find E is equal to HV. So in there,
See, you have to find energy using h nu. So Planck's constant, frequency is given in SI unit only, so you don't need to convert it into anything. Your final answer will be in terms of joules only. So if you want to calculate in terms of electron volts, you can divide it by. But right now, calculate in terms of joules only.
okay.
This is the answer to which part? First part or the second part? Okay, let's discuss it now. Frequency is given 6 into 10 to the power 14 hertz. This is the frequency given, and power is given to you as 2 into 10 to the power minus 3 watts. See, energy of each photon. How do you calculate energy of each photon? By taking the product of Planck's constant and the frequency. Planck's constant is 6.63 into 10 to the power minus 34 joule seconds, and your frequency is 6 into 10 to the power 14. So energy becomes 3.98 into 10 to the power minus, this will be 19, not 30. This will be 10 to the power minus 19. So 3.98 into 10 to the power minus 19. So this is the energy. Now in the second part, it has asked you to calculate how many photons per second on an average are emitted by the source. So power is what? Power is equal to number of photons multiplied by the energy of each photon. So N is equal to what? N is equal to power
P
by
by
P by E. So power is 2 into 10 to the power minus 3. what this is given to you. And energy is what? Energy you have already calculated in the first part, 3.98 into 10 to the power minus 19. So this will be 5 into 10 to the power 15 photons per second. So how much your energy came?
Yeah, I got some mistake here.
Not.
The first one.
Okay. See, the question says what? The question says that energy from the sun is received on earth at the rate of 2 calorie per centimeter square per minute. So rate of energy received from the sun. Rate of energy received from the sun. So this is equal to what? 2 calorie per centimeter square per minute. We have to convert it into SI unit because calorie cannot be considered. Now see, if you multiply 2 into 4.2, you will get 8.4 joules per centimeter square per minute. All right. Now see, energy of a photon received from sun is what? You have the wavelength of the solar light is given to you as 5500 angstrom. So
Yeah, that will
wavelength
be
will be what?
uh,
5500
E is equal
angstrom.
to H in your will take.
Yes, E is equal to hc by lambda. So from E is equal to hc by lambda. H is 6.63 into 10 to the power minus 34. 3 is 3 into 10 to the power 8 divided by the wavelength 5500 into 10 to the power minus 10 meter in terms of. So you will get the answer if you solve this, you calculate this, you will get it as 3.6 into 10 to the power minus 19 joules. All right. Now see if n is the number of photons reaching the earth per centimeter square per minute. Because we have the answer in terms of, we have the radiation rate given as in terms of per centimeter square per minute. So we have to keep in mind that n, if we take n as the number of photons, n is the number of photons reaching the earth, this is per centimeter square per minute. So total energy will be what? NE, total energy means 3.6 into 10 to the power minus 19. See, this is the energy of a photon received from sun. So if n is the number of photons, you have to multiply it with n, which is equal to the total energy received. So total energy received is what? 8.4 cent per centimeter square and rest of the terms. And see, here also you have it. So n will be what? 8.4 divided by 3.6. 8.4 divided by 3.6 into 10 to the power minus 19. So this will be approximately 2.3 into 10 to the power. This will become minus 19 will become positive 9. 19. This will be the number of photons.
Share here first which formula we have to use.
See, you have to use Einstein's photoelectric equation. Then only you will be able to connect all the three. Frequency is given. If photoelectrons are to be emitted from a potassium surface with a speed. So see, as soon as you see the term speed in your questions, remember that it is relating to you with kinetic energy. And with the help of kinetic energy, you have to use Einstein's photoelectric. So for mass, take 9.1 into 10 to the power minus 21. See, frequency is what? Frequency is not frequency. The speed is given to you. Speed is given to you as 6.6 6 into 10 to the power 6 meter per second. See, this is the speed given to you.
I use kinetic energy formula.
Yes,
Of
yes.
mv
So,
square.
so what's your answer coming?
After using kinetic energy, I am getting like I didn't use that EV formula. Like you have to convert into EV, right? First,
EV, electron volt.
yeah.
No, no need to convert it into electron volt.
Yeah, I got 163.8 into 10 raised to minus 19. I'm just using kinetic energy.
So you have just used kinetic energy.
Yes.
How much?
163.8 into 10 raised to minus 19.
Okay, let's just discuss it once and you can see where you got stuck. Now see, velocity is 6 into 10 to the power 6. And see, threshold frequency, this is given as 4.22 into 10 to the power 14 hertz. So Planck's constant, and mass of electron is given as 9.1 into 10 to the power minus 31 kg. Now see, from Einstein's photoelectric equation, if you remember, half mv square, this was equal to what? Kinetic energy. See, Einstein's photoelectric equation says that the total energy, this is equal to the sum of kinetic energy plus the work function. So if you have to find out kinetic energy, what will the kinetic energy be? Energy minus the work function. So energy is what? H nu. Threshold wavelength, this work function is equal to h nu naught.
Yeah, I
All
thought
right.
that.
Yes, so if you take h common, this will be nu minus nu naught. This is the formula that you had to consider. Okay, whenever velocity is given, remember Einstein's equation. Now see, if you put the terms, we have to find out velocity, no? So let's not velocity, we have to find out the frequency. We have to find out the frequency of the radiation. Means this. So see, h will go over here in the denominator. This will be h nu minus nu naught. So h will go. This will be nu minus nu naught. This will be mv square divided by 2h. Now see, this will also go. So frequency will be what? mv square divided by 2h plus the threshold frequency. This is now what you have to put in the values. Now see, frequency will be what? Mass is 9.1 into 10 to the power minus 31. V square, this is 6 into 10 to the power 6 whole square, V square. 2 multiplied by Planck's constant, 6.63 into 10 to the power minus 34, plus the threshold frequency, that is 4.22 into 10 to the power 14. Now you had to solve this to get the final frequency. So see, once you will solve this part, this portion, this will be equal to 2.48 into 10 to the power 14, plus add this 4.22 into 10 to the power 14. So your final frequency will be 6.7 into 10 to the power 14 hertz. Clear how to use this?
Yes.
All right, so just note it down.